This is the current architecture for the visualization application. It has a number of web application deployment cells, which has the Django web applications configured and deployed on them. There is a pool of memcached servers, and which have the memcached daemon running on them. There are two database machines with three databases, one for the authentication and page word count application, one for storing information on the earthquake application, the other one for machine learning and data for the Dota2 online platform. There is a host that runs the message broker for asynchronous tasks, and there are two Celery host machines which run the Celery worker tasks, and there is a load balancer which balances the requests that come in from the user or from the client side. Before going into the details of this particular architecture, let's have a look at the application itself. The application has a machine learning component, the Dota2 online visualization for the online gaming platform. It provides a visualization for a number of use cases. So this is the visualization for comparing two players, and the values are fetched live over the web from a REST API exposed by the Dota2 platform. This also has a machine learning item-to-item hero recommender, which recommends heroes for different players. This is done by building a co-occurrence matrix, and it works on the history of the usage of each individual hero and also the play history of individual players. So the earthquake application stores information about the earthquakes from the USGS website. This is also consuming a REST API provided by USGS, and the primary application is the word count application, which we have seen in multiple posts before. We can ask the application to generate the word count on web pages, and once we post it, we can see that it has started performing the word count, and the status is continuously updated, and the heavy work of accessing web pages, doing the word count and everything is done on Celery worker tasks. Now let's look at the architecture of the application and see how it helps to get the work done. The database, as we have seen, is distributed over two machines, and there are three primary databases, one for Dota2, one for authentication and page word counts, and one for the earthquake. The web application deployment cells are the virtual machines that are the application servers. They run the Django applications. They talk to the databases. As we have multiple databases, we need a database router, which is configured for the Django applications, and the queries that are targeting, let's say, the Dota2 database, which will be routed to that particular host, and the ones that target authentication and page word count are directed to the first host. And we also have memcached sitting between the databases and the application. We have two host machines running memcached daemon service for caching, and the web application consults the memcached pool first before accessing the database, and if it is a cache miss, the application will load the information from the database and update the cache itself. And there are a number of tasks that are performed asynchronously in this particular application. To speed it up, that is sent through a message broker to Celery worker hosts. So the message broker used here is RabbitMQ running on one server on a separate virtual machine running Ubuntu server 16.04, and that is configured with multiple queues. So Celery architecture inside this application is configured with multiple queues. There is a red queue, a blue queue, and a green one for use by the applications. And the default queue that comes with Celery is maintained as such for performing database cleanup and other tasks. And the reason for having color-coded queues is that Celery as such does not have the notion of prioritized tasks. So the red queue will be used by applications which have a top high priority task but are of low frequency. And the green queue will be used by the applications which have high frequency tasks, but the priority of the tasks is like low. And the blue queue for tasks anywhere in between that particular extremes. And we have two Celery hosts within this particular application. Each one is a virtual machine with the Celery service running on it, configured to consume particular queues and use it workers on that particular queue. So there is one host that is configured to just consume the default queue. The reason being that there is quite a lot of tasks that Celery fires up as part of its own housekeeping. And we have a number of cleanup tasks also. So that's the purpose of that particular host, and it does not touch the message queues for the application. And the other host number 2, has workers which are consuming all of the application queues. And the red queue has the task that we saw just now, which is the page word count, and the rest of the application's tasks are split on the blue and green queues. And the worker queues, the worker tasks talk to hosts on the internet for REST API consumption, for example, for Dota 2, and it also brings in information from like USGS. So all that is done by the worker tasks, and they have to update the database, so they need to know which database to talk to. So all that again goes through the database router configuration and the database routers that live inside the application. And there are two ways in which this application can easily address scaling requirements. For example, let's say that we have an increased number of requests for the page word count application, and we are seeing a substantial increase in that task, and the number of tasks that are being fired. So one approach would be to the way that this architecture will address that kind of scaling requirement is that we can start a virtual machine, add it to the Celery worker pool as another host, let's say host number 3, and that can be configured to just handle the red queue as we see here. And that's the queue where the page word counting task is being done. And this can be done for any combination of these queues, so that as per the requirements we can have another Celery host added to handle the tasks from those particular queues only. And there is one example where the architecture helps to scale. Another one is, let's say we want to support an additional number of requests per second or a higher number of users for a particular high load time. The solution is to add web application deployment cells to this particular pool. Instead of having like 2 or 3 web application servers, just add another 4 during peak time or as per the requirement. And in addition to adding the web application cells, we should also add memcached hosts. As the number of cells goes on increasing, each of those web application servers are actually accessing the memcached hosts. So if we want to keep the memcached pool as effectively utilized. We need to add hosts as and when required based on the number of requests coming into this particular pool. So those are two examples where this particular architecture can help to scale for task requirements and also for supporting different users and for performance requirements. Of course, the database has itself been designed to be distributed on multiple servers, so we would not have to split the database again. For example, if we have reached the upper limit of this particular part of the architecture, if you are supporting like uh, 10, 10 to 20 million users and that kind of load, then we can still achieve it with this kind of architecture, but it would be better uh, to use something like a distributed database, which is distributed by itself, like MongoDB. But for most requirements, this type of distributed architecture, by splitting the data across multiple databases, would help. And here it is done as part of the design from scratch. So we don't need to worry about that much. So that's it for the current architecture for this particular application and how it can scale.